We all know the graphs of a straight line, a parabola, and a hyperbola. In mathematics, functions can be represented by these graphs. So, what is function? It is similar to the principle the computer operates, that is, input, process, and then output. In this input, process, output device, we input 1. After processing, the outcome, 3, is the output. When the input is 0, after processing, the output is 1. When the input is -1, after processing, the output is -1. When we input a value x, the input, process, output device will then output a value y. We can see from this input, process, output device, the values of x and y are varied. In mathematics, x and y are both known as variable. Let's look again at x and y in this input, process, output context. The variable x inputted can be chosen freely, so x is called independent variable. However, if we look at the variable output y, the change in y is exactly dependent on x. Also, y cannot vary by itself. Therefore, y is called dependent variable. We can also use mapping to represent the relationship between x and y in the equation y equals to 2x plus 1. In this graph, y equals to 2x plus 1, we can clearly see that when x is any value, y is a value too, and it is a corresponding value. That is to say, when x equals to 1, there is one and only one corresponding value, and that is y equals to 3. For each value of x, there is exactly one corresponding value of y. Then we say y is the function of x. If we define function in mathematical language, then we say, if the variable y is determined by the variable x, that is to say, for each value of an independent variable, there is exactly one corresponding value of the dependent variable. So the dependent variable y is the function of the independent variable x. Function can be represented by equation. For example, y equals to 2x plus 1. We can use functional notation. The notation of function, we usually put it this way. Y equals 2x plus 1. And it is written as, we can read it this way. The function of x equals to 2x plus 1. In our daily lives, we can use function to represent the relationship between two or more variables. Look at this example. We all know how to calculate the perimeter of a square. The perimeter of a square is equal to 4 times of the length of one side. The perimeter of the square depends on the length of the side. If the side of the square is 1 cm, the perimeter is 4 cm. If the side is 2 cm, the perimeter is 8 cm. If the side is 3 cm, the perimeter is 12 cm. As such, when the length of the side varies, the perimeter of the square varies accordingly. If we use P equals to 4 times L to indicate the perimeter of the square, then P is the function of L. The mapping is used to represent P equals to 4L. That is, the relationship between P and L. Having said that, since variable x and variable y are also relative, the independent variable and the dependent variable are relative. Let's take a look at another example of function, x equals to y squared. A mapping is used to represent the relationship between y and x in x equals to y squared. We can clearly see that for each value of the independent variable y, there is exactly one corresponding value of the dependent variable x. For example, y is -1. There will be only one corresponding value, and that is x equals to 1. In this example, x is the function of y. To indicate this with a functional notation, it is like this. Irrespective of the situation, so long as we can identify which variable is the independent variable and which one is the dependent variable, we will be able to determine the function. We can browse these websites to learn more about the history of function. Let us go back to the example of y equals to 2x plus 1. There are many possible values for the independent variable x. -1, -1 over 3, 6.3, 22, etc. can all be values of the independent variable x. The collection of values of independent variable is called the domain of the function. At the same time, in function, the dependent variable y has a corresponding value. The collection of all values of the dependent variable is called codomain of the function. Let's look again at the function of y equals to 2x plus 1. If the domain is the collection of all real numbers, the codomain is also the collection of real numbers. If the domain is imaginary numbers or complex numbers, then the codomain is the corresponding imaginary numbers or complex numbers. Except under special circumstances, the codomain includes only real numbers in the function discussed in this program. In the example of the perimeter of a square, where p is equal to 4l, the length of a side is a positive number. That is, the domain contains all positive numbers. Now, the perimeter is correspondingly a positive number. That is, the codomain contains all positive numbers. Next, let's discuss other examples of domain and codomain. There is a function. Function x is equal to x squared plus 1. Any real number can be chosen as x. Then the domain of this function contains all real numbers, while the codomain contains all real numbers greater than or equal to 1. In another example, function x is equal to 1 over x. The domain does not contain all real numbers, because when x is 0, 1 over 0 is not defined. In order to give meaning to this function, the domain contains all real numbers except 0, while the codomain contains all real numbers. There are 3 ways to represent a function, namely algebraic method, tabular method, and graphical method. If we look again at the example of a function, we know that p is the function of L. The relationship between p and L, represented by algebraic method, is like this. By tabular method, it's like this. By graphical method, it's like this. By the way, in order to determine whether a certain graph is a function, that is, whether y is a function of x, all we need to do is to draw a perpendicular line at any value of x, that is the independent variable. If the perpendicular line cuts the graph at only one point, then this graph represents a function. We can explain this by the definition of function itself. Let us look at this graph. The perpendicular line cuts the graph at more than one point. It is not a function. The commonly seen graph of functions include graph of constant function, graph of linear function, graph of quadratic function. Next, we shall discuss the graphs of quadratic function. The way to represent quadratic function, y equals to ax squared plus bx plus c, or the function of x is equal to ax squared plus bx plus c, of which a is not equal to 0. Then the graph is parabola. In this function, if a is greater than 0, its graph opens upwards, while the vertex of the graph is at the lowest point. We call this lowest point the minimum point. If we draw a perpendicular line from this point, this line is known as the axis of symmetry. HK is the coordinate of the minimum point. The axis of symmetry can be derived from x coordinate. Then the numeral value of y coordinate is the minimum value. The parabola will intersect with y-axis at the point 0c. Therefore, the y-intercept of this graph of quadratic function is c. Let's take a look at this example of quadratic function, where the direction of opening of the parabola faces upwards. Y equals to x squared minus 2x minus 5. The vertex is 1 minus 6. The axis of symmetry is x equals to 1. The minimum value is minus 6. The y-intercept is minus 5. In the graph of quadratic function just mentioned, a is greater than 0. On the contrary, if a is less than 0, the direction of the opening of the parabola should face downwards. The vertex becomes the highest point of the graph, and we call this highest point the maximum point. If we draw a perpendicular line from this point, it gives us the axis of symmetry. HK is the coordinate of the maximum point. An axis of symmetry can be derived from using the x-coordinate. The numeral value of the y-coordinate is the maximum value. The parabola cuts y-axis at the point 0c. Therefore, the y-intercept of this graph of quadratic function is c. Using an example of the quadratic function where the direction of opening of the parabola faces downwards, y equals to minus x squared plus 2x plus 1. The vertex is 1, 2. The axis of symmetry is x equals to 1. The maximum value is 2. The y-intercept is 1. Whether the direction of opening of the parabola faces upwards or downwards, there are 3 possibilities to the numbers of x-intercepts: 2, 1, or none. The x-intercepts are in fact the roots of the quadratic equation, so the number of x-intercept is determined by the discriminant of the quadratic equation. When the discriminant is greater than 0, there are 2 x-intercepts. When the discriminant is equal to 0, there is only 1 x-intercept. When the discriminant is less than 0, there is no x-intercept. Other than reading the graph of the quadratic function, we can observe the various features of the graph, including the vertex, the axis of symmetry, the maximum value, the minimum value, and the y-intercept. Even if we don't draw the graph, we can use calculation to find these features. Completing the square can be used to convert the original equation into another form of equation. If a is greater than 0, the vertex is HK, y-intercept is c, the axis of symmetry is x equals to h, the minimum value is k. If a is less than 0, the vertex is HK, y-intercept is c, the axis of symmetry is x equals to h, the maximum value is k. Let us look at the following example. Instead of drawing the graph, we only use completing the square to convert the original equation into another form, and then find out the vertex, the y-intercept, the axis of symmetry, and the maximum and minimum values. Y equals to 2x squared plus 4x minus 1. The vertex is minus 1 minus 3. The y-intercept is minus 1. The axis of symmetry is x equals to minus 1. The minimum value is minus 3. Y equals to minus 5x squared plus 10x plus 18. The vertex is 1, 23. The y-intercept is 18. The axis of symmetry is x equals to 1. The maximum value is 23. Now, let's discuss the graphs of exponential function and logarithmic function. If a function can be written in the form function of x is equal to k times a to the power x, while a is greater than 0, a is not equal to 1, and k is not equal to 0, then this is an exponential function. This is a graph of an exponential function. The graph cuts the y-axis at the point 0k. Because k is greater than 0, the graph lies above the x-axis, and the graph neither has a maximum point, a minimum point, nor an axis of symmetry. As the value of x increases, the value of k times a to the power x also increases. As the value of x decreases indefinitely, the value of k times a to the power x gets closer and closer to 0. As the value of x increases, the rate of increase of k times a to the power x increases. That is, the curve tends to a perpendicular development. Let us look again at this functional graph. Function of x equals to k times a to the power x. When the value of a increases, the graphs get closer and closer to the y-axis at the top, tending to a perpendicular development. At the same time, the graphs get closer and closer to the x-axis on the left, tending to a horizontal development. Let us look at another graph of an exponential function, in which a is greater than 0 but less than 1, and k is not equal to 0. The graph cuts the y-axis at the point 0k because k is greater than 0. The graph lies above the x-axis, and the graph neither has a maximum point, a minimum point, nor an axis of symmetry. As the value of x increases, the value of k times a to the power x decreases. As the value of x increases indefinitely, the value of k times a to the power x gets closer and closer to 0. As the value of x increases, the rate of decrease of k times a to the power x decreases. That is, the graph tends to a horizontal development. If we compare the change in the value of a against the change in the development of graphs of the exponential function, we can see that as the value of a decreases, the graphs get closer and closer to the x-axis, tending to a horizontal development. At the same time, the graphs get closer and closer to the y-axis at the top, tending to a perpendicular development. We have learned about the graphs of exponential functions. Next, we shall explore further. Within the exponential function, what is the relationship between the change in k and a and the features of the graph? Here, we have two graphs of exponential functions. It seems like the graph above is a mirror image of the graph below. The values of a are the same in the two exponential functions. When the value of k is a positive number in an exponential function, the value of k is a negative number in another exponential function. The two graphs become a reflectional symmetry about the x-axis. In these two exponential function graphs, the left graph is a mirror image of the graph on the right. The values of k are the same in the two exponential functions. When the value of a in an exponential function is the reciprocal of the value of a in another exponential function, the two graphs have a reflectional symmetry about the y-axis. There is an inverse function of exponential function, that is, logarithmic function. Logarithmic function is function of x equals logarithm of x to the base a. It is written like this. In logarithmic function, the value of x must be greater than 0. There is a graph of a logarithmic function, where a is greater than 1. The graph cuts the y-axis at the point 1, 0. The graph lies on the right side of y-axis. The graph neither has a maximum point, a minimum point, nor an axis of symmetry. When x is greater than 0 but less than 1, logarithm of x to the base a is less than 0. The graph lies below the y-axis. When x is greater than 1, logarithm of x to the base a is greater than 0. The graph lies above the x-axis. As the value of x increases, the value of logarithm of x to the base a increases. When the value of x approaches 0, the value of logarithm of x to the base a decreases indefinitely. As the value of x increases, the rate of increase of logarithm of x to the base a decreases. The graph tends to a horizontal development. Let's look again at this graph of logarithmic function. As the value of a increases, the graphs get closer and closer to the y-axis, tending to a perpendicular development. At the same time, the graphs get closer and closer to the x-axis, tending to a horizontal development. Looking further at another graph of a logarithmic function, where a is greater than 0 but less than 1. The graph cuts the y-axis at the point 1, 0. The graph lies on the right of the y-axis. The graph neither has a maximum point, a minimum point, nor an axis of symmetry. When x is greater than 0 but less than 1, logarithm of x to the base a is greater than 0. The graph lies above the x-axis. When x is greater than 1, logarithm of x to the base a is less than 0. The graph lies below the x-axis. As the value of x increases, the value of logarithm of x to the base a decreases. When the value of x approaches 0, the value of logarithm of x to the base a increases indefinitely. As the value of x increases, the rate of decrease of logarithm of x to the base a decreases. If we compare the change in the value of a with the change in the graph of the logarithmic function, we can see that when the value of a decreases, the graphs get closer and closer to the y-axis, tending to a perpendicular development. At the same time, the graphs get closer and closer to the x-axis, tending to a horizontal development. The domain of logarithmic functions includes all positive real numbers. When x is less than or equal to 0, the function is undefined. The graph never cuts the y-axis. Next, let's see that inside the logarithmic function, what is the relationship between the change of a and the features of the graph? For these two logarithmic functions, the graph above is the mirror image of the graph below. When the value of a in the logarithmic function is the reciprocal of the value of a in another logarithmic function, the two graphs have a reflectional symmetry about the x-axis. It has been mentioned earlier that the exponential function is the inverse function of the logarithmic function and vice versa. As such, what are the observations of the respective graphs of an exponential function and a logarithmic function on the same Cartesian coordinate? The two graphs have a reflectional symmetry of each other about the straight line x equals to y. We have gone through the various graphs on the Cartesian coordinate and features of linear functions, quadratic functions, exponential functions, and logarithmic functions. Finally, let's see what the graph is like after a change in the functions. First, adding a positive real number k to the function, that is, the dependent variable plus k, a new functional graph will translate upwards by k units. If the previous positive real number k is subtracted from the function, that is the dependent variable minus k, the new functional graph will translate downwards by k units. Under the second case, that is originally, the function of x becomes the function of x plus k, that is the independent variable plus k. The graph of this new function will translate to the left by k units. If the original function of x becomes the function of x minus k, that is the independent variable minus k, the graph of this new function will translate to the right by k units. The third case is the function of a positive real number k times x, while k is greater than 1. That is the dependent variable times k. The graph of this new function will enlarge along the y-axis to k times of the graph of the original function. The opening of the graph becomes narrower. When the function is divided by a positive real number k, while k is greater than 1, that is the dependent variable is divided by k, the graph of this new function will reduce along the y-axis to 1 over k of the graph of the original function. In the fourth case, the new function is the original function of x becomes the function of k times x, while k is greater than 1. that is the independent variable, times k. The graph of this new function will reduce along the x-axis to 1 over k of the graph of the original function. If the original function of x becomes the function of x over k, while k is greater than 1, that is, the independent variable is divided by k, the graph of this new function will enlarge along the x-axis to k times of the graph of the original function. In this program, we have mainly discussed the relevant intuitive knowledge of functions and graphs. As to the part of calculation, you can explore further with your teacher or fellow students. If we use function as an example, mathematical knowledge and the form of representation are not independent from each other. Geometry and algebra are interrelated, only that the same concept is represented in different ways. I hope we can link up the mathematical knowledge we've acquired and own them, so that learning mathematics can be fun.